Hello students, we are going to discuss very important topic of the chapter chemical bonding. In the last class, we are discussing regarding the valency bond theory, which gives about the hybridization of the molecule, the shape of the molecule, the bond angle of the molecule. We discussed. But this valence bond theory could not explain the nature of bonds, that the strength of bond, the number of bonds produced in the molecule, and what is the magnetic character of the diatomic molecules or polyatomic molecules, and how the atomic orbitals take part in the bond formation. Then during overlapping of atomic orbitals, what are the different types of orbitals produced? This concept could not explain by the valence bond theory. But the new concept, that is MOT, molecular orbital theory, can explain the nature of bonds, the magnetic character of the molecule, and the strength of the bond. So many things we will discuss. Now, how the atomic orbitals combine, overlap each other, forming forming the same type of orbitals or different type of orbitals, and what are the shape of the orbital produced during overlapping of atomic orbitals. Let us discuss things. So according to MOT, molecular orbital theory, valence shell atomic orbitals, that means atomic orbitals of valence shell, outermost valence shell atomic orbitals of different atoms overlap, forming a molecular orbitals. Very important this thing. That means during overlapping of atomic orbitals, forming molecular orbitals. And this molecular orbital is polycentric. It is polycentric. Polycentric means it is produced in between different atoms, two or more atoms. That's why the atomic orbitals of the atoms, bonded atoms, overlap each other, forming molecular orbitals. This molecular orbital remains in between bonded atoms. That's why it is called polycentric. But atomic orbital is always monocentric. It belongs to the particular atom. But molecular orbital, it belongs to the bonded atoms. That's why it is called polycentric. And the number of molecular orbital produced during overlapping of atomic orbitals, it is always same as the number of atomic orbitals combined. Number of atom orbitals combined produce the same number of molecular orbitals. That is a very important thing during combination. And the two types of molecular orbitals are produced during overlapping of atomic orbitals. When atomic orbital overlaps, generally two types of molecular orbitals are produced. One is called bonding molecular orbital, another is antibonding molecular orbital. We remember bonding has already written, bonding molecular orbital has lower energy and more stable. Lower energy means it is more stable. Bonding molecular orbital has lower energy than antibonding molecular orbital. That means during the formation of molecular orbital, two types of molecular orbital are produced. Overlapping of atomic orbital produce molecular orbital. There are two types of molecular orbital produced. One is bonding, another is antibonding. And bonding orbital has lower energy than the antibonding molecular orbital. Then another important concept is that rules that during overlapping of atomic orbitals, how it will produce bonding, how it will produce antibonding, that is explained like this. During overlapping this bonding, that atomic orbitals, if the atomic orbitals having closer energy, we can say, and having same symmetry, if they have same symmetry, that means arrangement is same. If the symmetry is same, then produce bonding molecular orbitals. Same symmetry orbitals produce bonding molecular orbitals. Symmetry must be same. Then, how many types of bonding orbitals generally produce? It may be a sigma bond, it may be a pi bond. Already you know. So there are two types of molecular orbital produced, either a sigma or pi. Molecular orbital generally two types. In terms of energy, it is bonding or antibonding, but generally in the nature it is two types. Either a sigma, if it produce sigma bonded, either when it produce sigma bond, that is called sigma molecular orbitals. It produce pi bond, that is called pi molecular orbitals. So depends upon the nature of bond. Already I have told you, molecular orbital gives the idea about the nature of bond. So when it produce that axial overlapping, that molecular orbital is called sigma bond. And when it overlap sidewise, then produce pi molecular orbitals. So sigma molecular orbitals or pi molecular orbitals produced during overlapping of atomic orbitals. But molecular orbitals, on the basis of their energy, on the basis of their stability, it is maybe bonding or antibonding. That means sigma has bonding and antibonding. That means it may be sigma, sigma star, pi, pi star. Remember, that is generally two types of molecular orbital produced. One is bonding and antibonding. But if you see the nature of bond, either it is sigma bond or pi bond. On that basis, the molecular orbital may be sigma, sigma star. Sigma star indicates antibonding, and pi and pi star. Pi star indicates antibonding. Pi star antibonding molecular orbital. Sigma star means sigma antibonding molecular orbital. And only sigma pi indicates bonding sigma orbitals and pi bonding molecular orbitals. So these are the types of molecular orbitals. And during the overlapping of orbitals carry the electrons, maybe half filled or fully filled. So during the formation of molecular orbitals, the electron available in the molecular orbitals, it also obey the rules like the filling of electron in atom orbital, that is above principles, Fourn's rules, Pauli exclusion principle. All the rules it obey like atom orbital during filling of electron in molecular orbitals. So this point also very important. The overlapping of atomic orbital of different atoms follow the which rule, which method it follow during overlapping of atom orbital. This method is called LCAO method. LCAO means linear combination of atomic orbitals. LCAO. This linear combination of atomic orbitals, it mainly obey additive or subtractive method. Additive effect or subtractive effect. Addition mainly gives that is bonding orbitals, and subtractive method always gives antibonding molecular orbitals. So these two things are very important. During overlapping of atomic orbital, it is follow the LCAO method, that is additive method or subtractive method. Additive method always produce bonding and subtractive method always produce antibonding. Then this MOT gives the idea of bond order. How many types, how many number of bonds available in the bonded atoms, we can know from bond order, and the stability of the atom or ions, and the magnetic nature of the molecule we can know from the MOT. So this is the modern concept of the what? Covalent bonding, that's the combination of atoms. If you see from the beginning, if you study that already we have known that electrons, sharing of electrons and Lewis structure, like this octet rule satisfaction, like this method already you know. Then we have discussed that formation of sigma bond, pi bond by the overlapping of atom orbital, either axially or sideways overlapping. Then valence bond theory concept regarding the hybridization and the shape of the molecule, and that another concept, that is VSPR theory also, that having number of lone pair, number of one pair, then the shape of the molecule, like this we discussed. But MOT is the advanced concept which gives about the shape of the molecule, that the bond, nature of bonds and the magnetic character, every concept you can know from the MOT. So let us discuss some examples that you see when s orbitals overlap with another s orbitals. When s orbital overlap with another s orbitals, we know it will produce sigma bonds. S orbital always produce sigma bond. But during the formation of sigma bond, you have to see support is symmetry, is plus symmetry, this is your plus symmetry, then produce what? Then overlapping, it produce molecular orbitals, both carry what? Plus charge. This is the sigma bonding orbitals. You can write only sigma, don't be confused. So sigma SS always produce always produce sigma bond. This is sigma bond. But we know when two atoms, as per the rules, already have written that two types of molecular orbital produce. One is bonding and antibonding. And we written already number of molecular orbitals produced is equal to number of atomic orbitals combined. Here two atomic orbitals combined means it will produce two molecular orbitals. One is bonding, another is antibonding. Antibonding orbital will be like this. Like this. That means there will be no touch, there is no contact between the atomic orbitals. The separation will be more, that's why repulsion will be more, that's why energy will be increased. So this is called sigma star. So during combination of two atomic orbitals produce two molecular orbitals, one is bonding, another is antibonding. Similarly, when you take S overlap with P, you see the P, then produce two types of, one is, if I say like this, so suppose this plus minus, so this is plus, this is minus, and this is your what? Molecular orbitals. This side will be large size, this is your sigma bonding. But how to produce antibonding? So S orbital combine with P orbitals always produce sigma bond. This is sigma bonding. Antibonding will be like this. This is plus, this is minus, plus. This is sigma star. Okay. Similarly, P orbital plus minus minus plus, when combined it will produce bonding Suppose this is plus, this is plus, this is minus. Minus minus, so sigma bonding. Antibonding will be remain same. Plus minus plus minus. So this is sigma start. So this is bonding sigma, antibonding sigma. Similarly, pi bond is produced when p orbitals mix with another p orbitals. Suppose this is plus minus. It produces bonding and antibonding. Bonding will be upside is plus and lower part is minus. Lower part is minus. So this is pi bonding. Antibonding will be that there is no overlap here. So we can say like this: plus minus plus. This is your antibonding pi star. So in this way, bonding and antibonding orbitals produce. So this overlapping orbitals always obey LCAO method. LCAO method. As per the MOT concept, it must obey LCAO. LCAO method is two. That is, one is additive method. Second one is subtractive method. Additive method and is subtractive method. Additive method, it mainly same symmetry. When same symmetry orbitals overlap, forming what? Bonding. When different symmetry or atomic orbitals come closer, that is called subtractive method. That is here forming antibonding. For example, here suppose psi A mixed with psi B, that is additive method, forming psi AB bonding, and psi A and psi B, and psi is the atomic orbital. Psi, this minus indicates subtractive method, produce antibonding. That is bonding. You can say this is bonding, this is antibonding. And here, if you see, during just overlapping, if you see, then the electron density during overlapping will be more. And if you see just combination, for example, this is your this orbital mixed with another orbitals, plus minus. When they mix, it produce during combination. As they are both same symmetry, so it gives plus minus. So the overlapping region will be more because plus combined with plus, minus combined with minus. But when it will be subtractive method, if you see the subtractive method, then what happens? It will be reduced. The result will be reduced. Plus and minus. That means here what happens? During subtraction, the region will be decreased. The overlap region will be less. But in addition method, overlap, that is, we can say, that is, interference of waves. When two waves can be added, two waves can be subtracted, then the amplitude of wave can be increased or decreased. During addition, amplitude increases. This is increasing of amplitude above and below, and this is decreasing the amplitude. When both will be subtracted, then the amplitude will be decreased. Very less value will come. during addition, both subtraction value will be less. So this you can say this is your bonding. This you can say this is bonding. You can say this is bonding, and this is your antibonding. In this way, addition of wave takes place, and orbitals can be added, orbital can be subtracted. So additive method and subtractive method. So this is regarding LCAO method. Then next we will discuss the formation of the sigma bond and pi bond. Okay. Now we will discuss how some diatomic molecules are produced by molecular orbital theory concept. Already discussed that atomic orbitals combine to form molecular orbitals. During combination, it produces bonding orbital and antibonding orbitals. For example, let us take that hydrogen molecule, formation of hydrogen molecule. Hydrogen molecules, if you see, it has two atoms, hydrogen atoms. This is the hydrogen atoms, H, and another this is H. And hydrogen atom, if you see, it has only 1s orbitals, that is 1s1, 1s1. This is also hydrogen atom, 1s1, overlaps. These two hydrogen atoms when combined, forming, already you know, when atomic orbitals overlap, forming molecular orbitals, as two atomic orbitals overlapping, forming two molecular orbitals. One is bonding, has lower energy, then another is antibonding, has higher energy. So this is your sigma, as S overlap always produce sigma orbitals. So this is sigma 1s, this is your sigma 1s star. Star indicates antibonding and sigma indicates bonding. But as 1s1 means 1 electron, 1s1 also 1 electron, both orbital having single electrons, when overlap forming molecular orbitals, one unpaired electron will combine to form molecular orbital. This one carry two electrons because lower energy as per the Wundt's rule. Here all electron first, what happens as per the Orbital principles, that as this sigma 1s bonding orbital has lower energy and sigma 1 star has higher energy, so all electron will be filled in sigma 1s and sigma 1 star will be 0. So this is the molecular orbitals and this is your atomic orbitals. This is the atomic orbital of hydrogen atom, H1, this is also H1. So in this way molecular orbital is produced. So if you write what is the configuration is sigma 1s2 and sigma 1s star 0. This is the configuration of hydrogen molecules. So if there is a rule, what within the 14 electrons, diatomic molecule having 14 electrons, up to 14 electrons, we have to follow during combination of, suppose here 1s, then 2s, then 2p, 1s, 2s and 2p, like this when overlap, because here 1s2, 2s2, that is how much? For that here 10 electrons, then 2p 3, 2 to 4 electron 3, that is 7 electrons. 7 means this is one atom having 7 electrons, one another atom combined it becomes 14 electrons. So we are discussing up to 14 electrons of the molecule. 14 14 electron of the molecule. So if the atom having 1s2, 2s2, 2p3, then when combined the same 1s2, 2s2 and 2p3, the result will be during mixing of 1s, 2s, 2p, 1s, 2s, 2p of other atoms. When they mix, this is one atom, this is another atom. When mixed, forming molecular orbitals, molecular orbital order is sigma 1s 2, then sigma 1 star 2, then sigma 2s2, then sigma 2s star 2. When 1s mix, bonding, antibonding. 2s mix, produce bonding, antibonding. Then remaining 2p. 2p, here there is a rule up to 14 electrons. First, pi bond will come, pi x 2, then pi y 2, then remaining sigma 2pz 2. Then it starts. This is about the 14 electrons. 2 plus 2, 2, that remaining up to this, it is 14 electrons. So this is the energy order of molecular orbital of diatomic molecule up to 14 electrons. Then more than 14 electrons, more than 14 electrons. Here what happens? Up to nitrogen what happens? Due to the sigma 1s and sigma 2pz orbital, due to more repulsion, energy increases. That's why it crushes over the pi x and pi y. That's energy, sigma energy always less than pi. Because sigma bond is more stable than pi bond. So energy of sigma bond is more less than the pi bond. But due to it is a special case that in case of 14 electron, in case of nitrogen, what happens? Sigma 2s and sigma 2pz orbital repulsion is more. Due to more repulsion, energy of sigma 2pz increases and it exceeds pi x pi. This exception, you remember this. This case is very important, remember this. The more than 14 is similar order. That sigma 1s2, sigma 1s star 2, then sigma 2s2, then sigma 2s star 2, then which will come as per the order. Sigma 2pz2, then pi x 2, then pi y2, more than 14. So let it be 16. You take the 16 like this. First this is the order. Then star, pi x star. Sorry, I have not written here. One thing I have forgotten to write this thing. Here star will be written. Here, which will come first. That sigma to pz2, then star. Star of this one. Pi x star 2. As it is up to 14, you write 0. This thing 0. This is 0. Then this equal to pi y star 0, then sigma to pz star 0. Up to 14 I have written. Up to 14 means 14. 14 will be finished at this point. More than 14, this is the order. Pi x 2, pi y 2, then pi x star 2, then pi y star 2, then sigma to pz star 2. That means up to 20. This is 20 electron. 20 electron, this is 14 electron. This order. So we have to follow this rule. Up to 14 this configuration and more than 14 this configuration we have to follow. So let us take the example that formation of, for example, suppose here I can write H2 plus. H2 configuration is sigma 1s2 sigma 1s star 0, and H2 plus means it has also losing one electron, so it becomes sigma 1s1 sigma 1s star 0. S2 minus, what is this? S2 minus will be 1 electron added. Minus means 1 electron added. So it will be added here. Sigma 1s2, sigma 1s2, then sigma 1 star 1 electron added. So this is the configuration. Then for nitrogen, if you take nitrogen molecule, as it has 14 electrons, already I have told you, 14 means same order, sigma 1s2, sigma 1s star 2, then sigma 2s2, then sigma 2s star 2, okay, then pi x 2 equal to pi y2, then sigma to pz2. You see 14, 2, 4 to 6 to 8, 10, 14 electrons. So this is the nitrogen molecule. If you write N2 plus, then 1 electron will be removed. 1 electron removed from, it will be removed from outermost molecular orbital, that is sigma. So sigma 1s2, sigma 1s star 2, sigma 2s2, sigma 2s star 2, pi x2, pi y2, sigma to pz1. This is the N2 plus. Then N2 minus, if you write, N2 minus means 1 electron added more than, N2 plus has 13 electrons, N2 minus has 15 electrons. But don't be confused, 15 means more than 14, no, don't follow this. Are it derived from nitrogen? Are this configuration will derive from nitrogen? What is the basic? What is the main formula? Main formula is N2. From N2 it is derived. That's why N2 minus means it will be added in N2. So N2 means it is the main molecule is N2. So 15 electron, it will be sigma 1s2, sigma 1s star 2, sigma 2s2, sigma star 2, then pi x2 equal to pi y2. That means energy same. That's why equal written. Then as here 1 electron is more, then this is already same, sigma to pz2. Then next is coming its star, what I have given. After sigma to pz, star will come. So it will become pi x star 1 and pi y star 0. 1 electron occupying this. So this is the configuration of N2 minus. Similarly, what is the configuration of oxygen O2? O2 molecule, as O2 molecule is 16 electron, so it will follow more than 14. So sigma 1s2, sigma 1s star 2, then sigma 2s2, sigma 2s star 2, then which is coming as for the more than 14, sigma 2pz will come. Sigma to pz2, then pi x2 equal to pi y2, then which is coming star. Star pi x star 1, then equal to pi star y1. You calculate how much, 16 or not? 2 plus 2, 4, to 6 to 8, 10, 10, 4, how much? 14 and 1, 1. It obey Ohm's rule. Already you have written in the emoji that postulates the features that it also obey the some rules like above principle, Ohm's rules, like atomic orbitals. So pi star 2 and pi star 0, y star 0, that is round. So 1, 1 will occupy first. So this is the sigma O2, then O2 plus will be same, sigma 1s2, sigma 1s star 2, sigma 2s2 sigma 2s star 2 sigma 2pz2, then pi x2 equal to pi y2, then pi x star 1 equal to pi y star 0. Because one electron will be lost. Then O2 minus will be sigma 1s2 sigma 1s star 2, then sigma 2s2 sigma 2s star 2 sigma 2pz2 pi x2 pi y2. Then as O2 minus derived from O2, one electron is more, that is O2 plus is 15 electron, O2 minus is 17 electron. One electron is more, so it will be 1 will occupy, then 2 2, then pi x star 2, then star. This is star. Pi star 2, then pi y star 1, remaining same. So this is your O2, O2 plus, O2 minus. We have to see in from which orbital electron will be lost. So this is the configuration of what? N2, N2 plus, N2 minus, H2, H2 plus, H2 minus, and O2, O2 plus, O2 minus. This is the configuration. Then we will see the what is the bond order. You see, bond order of any molecule or either particular bond, it is the what? Total bonding electron minus antibonding electron by 2. This is the formula. B means bonding electron, B means antibonding electron by 2. For example, suppose H2 molecule. H2 molecule, how many bonding? Bonding is 2, antibonding 0. So 2 minus 0 by 2, that is 1. So this is the bond order of H2 is 1. Similarly, what is the bond order of H2 plus? H2 plus, if you see, I have written here H2 plus only bonding is 1. So 1 minus 0 by 2, that is half. But you can start from here. As antibonding is 0, so electron is lost from bonding. So 1 minus 0. H2 minus means electron is added where already is fully occupied. Then 1 electron will be here. So 2 minus 1 by 2, that is half. This is the bond order of H2, H2 plus, H2 minus. So similarly, for N2 molecule, bond order of N2 molecule will be, N2 is like this. N2 is how many bonding electron you see? 2 to 4 to 6 to 8 to 10. So 10 minus how much antibonding? 2 plus 2, that is 4. 4 by 2, that is 3. Already know nitrogen having triple bond. N2 plus means from where electron is removed? Electron removed from where? Bonding. Because you see configuration. Last electron present in bonding. That's why it is 9 minus 4 by 2, that is half. That is 2 half. 2.5. Here N2 minus means, if you see, N2 minus last electron present in antibonding. So that is, it is produced from N2. So last electron goes to antibonding. Antibonding means here 10 minus 5 by 2. Because earlier it was 4 electron in bonding. As is N2 minus 1 electron added and it goes to antibonding. As go to antibonding, that's a 10 minus 5 by 2. That is how much? That is also same, 2.5. That is also 2.5. Similarly, what is the oxygen? Bond order of oxygen. technique I am telling, remember, technique is as oxygen is 16, the easy method is 10 minus 6 by 2, that is 2. O2 plus, O2 plus means electron will be lost from antibonding, you see. O2 plus, O2 the electron present in antibonding, so O2 plus means derived from oxygen. After losing one electron, it will be lost from antibonding. So 10 minus 5 by 2, that is 2.5. Then O2 minus 1 means electron is lost from, O2 minus means electron is not lost, it is electron gain in oxygen. Again, already there is antibonding, another electron is added because it is capacity 2. Already having one electron, so one electron can be added. So it will be 10 minus 6 by 2. O2 minus, as it has already antibonding electron 1, but O2 minus means another electron is already added here. That will be 10 minus 6 means 10 minus 7. It will be 10 minus 7. 10 minus 7 by 2, that is 1.5. So this is the bond order calculation. Okay. Then there is an important rule regarding the stability of the molecule and the mainly stability of the molecule as per the bond order. Let us discuss this thing. Then there is a relation between the stability of the molecule and its bond order. More bond order, more stable. If bond order is more, stability will be more. More antibonding electron, less stable. If antibonding electrons are more, then stability will be less. Then this is the very important thing. If this second point depends upon if bond order is same, then if antibonding orbital having more electrons, then stability will be less. So let us example that what is the stability of H2 plus, H2 minus. If you see the bond order already calculated, H2 1 half here. So you can write here what is the bond order. If you see H2 bond order is 1, H2 plus is half, H2 minus is half. So first H2 will come as per the stability highest. Here both is half, but which has more antibonding electron? You see here antibonding is 0, here antibonding is 1. That's why it is less stable. Then H2 plus, then H2 minus. There is a rule. More antibonding electron, less stable. Stability will be less. So here both having half bond order, but antibonding electron here 1, here 0. So it is less stable. Similarly come to that nitrogen. Nitrogen same 3, 2.5, 2.5. So 3 means nitrogen will come more stable. But N2 plus has 4 antibonding electron, but N2 minus has 5 antibonding electron. That's why it is less stable. N2 plus is more stable than N2 minus. So this is very important. This is the order of stability. This is the order of stability. Stability order. Here also stability. Then for oxygen 2, 2.5, 1.5. O2 plus is more stable than O2. O2 plus is more stable than O2, then O2 minus. So this is the what? Stability order. So bond order and stability, this concept could not explain by valence bond theory. So the bond order and stability concept is explained by MOT. So we can compare which atom or which ion is more stable. Then molecular orbital energy diagram. Molecular orbital energy diagram, MO energy diagram, if you do, sometimes it is also asking how can you draw the molecular orbital. Here, for example, let us take nitrogen molecule. Nitrogen molecule, if you take nitrogen molecule has two bonded atoms, Na and Nb. And nitrogen electron configuration is 1s2, then 2s2, then 2p3, 2p3. Here also same, 1s2, then 2s2, then 2p3, like this. I can draw this one. 1s combined produce bonding and antibonding. Then this one also produce bonding and antibonding. And this one also produce bond. How many here? 3. Each having two electrons. Each having two electrons. 2s2. Here one electron. 2p3. So bonding, one is bonding. Which bonding will come? That is pi. First pi will come. 2 pi. Then it's sigma. Then sigma is coming. Then star. Pi x star, pi y star for nitrogen. For nitrogen here pi x2, pi y2, then sigma. Bonding. Here you see bonding, then antibonding. Bonding, then this antibonding. So here 6 electron you can fill up here. 2, 2, 4, 2, 6. Here it will be 2, 2, here 2, 2, like this. So, and here vacant, another star also remaining, but star is just what? It is vacant. Sigma to pz star. This is your pi x and pi y star, also vacant. And this is your pi x is equal to pi y, and this is your sigma to pz. Just same way it is written. So this is the what? Molecular orbital. Similarly for oxygen molecule, if you draw for oxygen molecule, suppose this is your oxygen, you can draw 1s, 1s2, 2s2, then 2s, 2s2, 2s2, then 2p4. 2p4 can be written as like this. 2p4. Here also 2p4. 2p4 means 1, 2, 3, 4. 1, 2, 3, 4. Then I can fill up here bonding, antibonding, 2, 2, then bonding, okay, antibonding, 2, then 4, 2p4, 3, 3, 6 orbitals forming 6, 3 plus 3, 2p3 p3, 3p orbital forming 6 and molecular orbital. So as per the oxygen, first which is coming? Sigma. You see for oxygen which is coming? First sigma, then pi bond. So sigma, then pi, then pi, sigma, pi, then pi star, then sigma. So this is sigma 2pz, this is pi x, pi y, pi x star, pi y star, this is sigma 2pz star. Same as like the electronic configuration, we have to write a structure. So we have to join. this one, this one, this one, this one, this one, and this one. You have to join. Then fill up electron. So 4 electron, 2, 2, 4 electron, 2, 2. How many electron here? 4 plus 4, 8. So 2, 2, 2, 6, 1, 1, 8. So pi star 1, pi y star as per the Bool's law. So you see pi star 1, pi y star 1. And sigma 2 to z star is 0. No, vacant. It is vacant. So this is the N2 molecule. This is your O2 molecule. Energy diagram. This is the energy order. Energy diagram. Bonding, similar energy. Atomic orbital, atomic orbital, atomic orbital. This is the molecular orbital. Atomic orbital of oxygen. So oxygen A, oxygen B, and forming O2 molecule. And this is your molecular orbital. So in this way, you will practice so many molecules that and they are bonded. For example, sometimes question will ask why helium 2 is on does not exist. Does not exist. Question may be asked why helium 2 molecule doesn't exist. Because if you see helium molecule bond order, if you calculate the bond order of helium molecule, it will have like this. Helium 2 bond order. Helium 2 means total electron 4 plus 4, that is helium 2. Helium 2 means helium has 2 electron. Helium 2 means that is 4 electron. 4 means sigma 1s2 sigma 1s star 2. So bonding 2, antibonding 2. What is the bond order? If you calculate, bond order will be 2 minus 2 by 2, that is 0. When the bond order will be 0, that molecule, that ion does not exist. Remember this thing point. You can add this thing, third point. 0 bond order, molecule does not exist. Molecule does not exist. This is also one important point. More bond order, more stable. More antibonding electron, less stable. And 0 bond order, molecule does not exist. So this is regarding molecular orbital theory. So practice more examples, then we will have more knowledge about MOT and regarding the bond order and stability molecule. Okay, thank you all.